Okay, our topic is section 2.5, autonomous differential equations in popular dynamics. So we're going to ignore the unpopular. So first thing, what do we mean? We talk about autonomous equation. For that, it's going to follow this form. dy dt is a function of y. So whenever we do the derivative, it will depend on y being in it. So for example, if we had our exponential of e to the rt, then y prime is r e to the rt, which is r times y. So our derivative has y in it. So that's the type of thing. So these exponentials were autonomous. And actually, that's the next thing we'll look at is exponential growth. It could also be exponential decay. They usually just talk about growth, though, as in decay is a negative growth. And as we had up here, our dy dt is r times y. And we have some y at 0 is our y naught. And so whenever we are getting our final result, and our, oops, that doesn't go there. Our general case is given by that. And now if our r is greater than 0, that's growth. If our r is less than 0, that is our decay. And r is called the constant of proportionality. So there's our exponential growth. There are other ways we can look at this, or other forms of our autonomous equations, such as the growth. Now, logistic growth is similar in that our derivative is going to depend on y, but it's a function of y and times a y separately. So everything, every term has a y in it. So that's going to be important. There will be no just plus a constant, as there could be in other situations. So what we want is to choose our h of y so that it's equal to r is greater than 0 when y is small. So we want to find this function so that we can approximate it with just an r. So we can make our autonomous, or excuse me, our logistic one resemble an exponential growth for small y values. So here, we also want our h of y. Type it, it'll be a little bit easier and neater. We want h of y to decrease as y increases, and h of y to be greater, or excuse me, less than 0, very large y. So why do we want this to work this way? Is it will help to keep our dy dt from going crazy. So as one gets big, the other is getting small. So it helps to balance them out. Now it might not keep it as a constant, or might not make the growth, a linear, but it does help to balance it so it doesn't, you don't have both of them getting big and having our growth rate really go crazy. Now, one example that we can do with this is that we can let our h of y equal r minus ay, with our a being a positive number. So now, as y gets big, we are subtracting it, so that makes the whole thing get smaller. And whenever we get really big y values, this a times y is going to get eventually bigger than r, which does make it negative, which is accounting for our criteria that we want. So overall, what we end up with is our dy dt being equal to r minus ay times y. And if we factor out the r, it's 1 minus ky times y, where k is equal to a over r. Now this is known as the Verhulst equation, or the logistic equation. And r in this case is called the intrinsic growth rate. So it's a growth rate with no limiting factors to it. And we can use a slope field to graph y versus t. So it's basically doing our vector fields that we've done before, things like that. Now, when we do these, we're going to look for our equilibrium solutions. And with this, then, we're going to use our vector fields to help tell us some things about this. So when we set this equal to 0, so our equilibrium, our slope is equal to 0. And whoops, I made a mistake back here. This should be y over k. So k is r over a. I had it the other way around. This is what happens when you don't read your notes. Here we go. Easy correction. Make that look like a y up there. Okay. So it's y over k times y equals 0. So whenever we do this, we're going to have y equals what we call phi 1 of t. And that's going to equal 0. And then we'll also have phi equals phi 2 of t, which is k, which will be our solutions. And that's the reason why we want to write our equation in the Verhulst form, so that it's pretty easy that whenever y equals that k over k is 1, 1 minus 1 is 0, so we can get our equilibrium solution very easily. And so for the first one out front, whenever that y equals 0, that all works. And then whenever y equals k, that works. And so we're going to use the phi just as a way to name our functions, just so we can tell distinguish between the two, of having 1 and 2, rather than just calling both of them y, or a y1 and a y2. So now, building off of this, we're going to have our critical points, just like what you had before, and those are the zeros of this f of y equation. And so what we're going to do is draw what's called a phase line. And what this is that on the y-axis, it shows the direction of how y moves as t increases. And we're going to use y versus f of y. So be careful here. This is not a t versus y. This is not an x versus y. This is y and then our f of y. And so the f of y is basically your derivative. So it's basically y versus its derivative that we're graphing. So we just said that our derivative is going to have equilibrium points at 0 and k. It has 2 zeros. If we graph it out, it's going to be a very nice downward facing parabola where that apex, our peak, is going to be at k over 2. Now, when we use the equation, and it's pretty easy to actually picture this if you just go ahead and distribute everything. It's ay minus a over k. Make that a better looking k. Y squared. And then you can figure out that's k over y if you're using your negative b over 2a thing, or if you want to take another derivative of this and set equal to 0, you figure it out. But now we're worried about how things move. So we want to put arrows on the y-axis. So in this case, if we use less than k over 2, it moves towards k over 2. If we're bigger than that, it moves towards k, and bigger than that, it moves towards k. So how do we know this? It's going back to whenever we solve for our y and how we can make it a y of t and then see what's happening with that. But we don't even need to know what y is for the work because we know how y is changing with relation to t, because that's what our derivative is. So if you look out over on this, and let me get a better color. Over here, when we are bigger than k. If you plug that into the equation here, it'll be something bigger than k over k, which is bigger than 1. 1 minus something bigger than 1 is negative. That's positive, that's positive. So it's a positive times a negative times a positive, it's all negative. So our dy dt is decreasing. So therefore the y's here should be decreasing. So therefore they're going towards k. If we pick anything between 0 and k, then that part's positive. This part is less than 1. So therefore that's positive and that's positive. So they're all increasing. So we have a general movement upward. So that's how you can figure it out of using your dy dt in order to figure out whether you're going left and right, however it's working out. So we'll look at this in another form whenever we look for our critical threshold coming up with a different graph based on this. But there's our idea for our phase line. So it's going to be the graph of y prime versus y, and then we're going to also include what's happening on that y-axis in the direction it's moving. And we want our critical points to be represented. So another thing we want to look at is called saturation level. And another way we can think of this is your environmental capacity, or the upper bound of your population. So what is the largest amount of population that a region can sustain? So for example, back in the late 1800s, early 1900s, whenever the national parks were first founded, Yellowstone, up until it became a national park, had just existed as it existed, and the animals controlled population. The predators ate the prey ate the plant life, and circle of life, all that good stuff, and things balanced. When it became a national park, or when people started coming to Yellowstone, they wanted to see the herbivores mainly. They didn't want to see the wolves. So they started to hunt them off. They killed off so many of the wolves that the herbivore populations of the bison and the elk and the deer and whatever else just exploded. But they found out that the herds were not as healthy. And the populations did go up, but then they also declined after a bit, and because there were so many herbivores that ate too much food, and then they started to starve. So it was not advantageous for the herbivores. There was always so much of the population that the land could sustain before they ate it all out, and then the population did decline because they were starving to death. So what they found out is by reintroducing the wolves and other predators back into the system, they could help balance it better. But our saturation level is the uppermost limit of what a region could support by itself. So whenever we look at these, we're going to look at a couple of different things. There's type it asymptotically stable solutions. We will also have unstable equilibrium solutions, and then semi-stable solutions. We're going to break down our solutions based on what is happening. So for the asymptotically stable ones, we have the limit as t goes to infinity of this phi of t equals, in this case, our y equal phi of t. So it's one of our solutions does go to a value as our t goes to infinity. So we see that our graph is going towards it. And so then we would say that y equals k is asymptotically stable, or either an asymptotically stable equilibrium or an asymptotically stable critical point. Now it all comes into it's a asymptotically stable solution, but it has a little bit of a special name. Now, if it's unstable, the limit as t goes to infinity of phi 1 of t will not equal k when the limit as t goes to infinity of phi 2 of k of t does equal k. So the limit for one of them is different than the limit for all the other starting points. So one starting point goes one place, every other starting point goes somewhere else. And this will be an unstable equilibrium or an unstable critical point. So in this, both sides are going to go to k. for the unstable one, neither side will go to K. And for semi-stable, one side goes to K and one side will not. And we'll see what I mean by one side in a second. But stable, both go to it. Unstable, neither goes to it. Semi-stable, one does, one doesn't. So there's your breakdown. So whenever we do this, we're going to draw some other graphs. We look for what's called a critical threshold. And so our threshold level is going to be a value for y in which the solutions above and below have different limits. So we're looking for where we get our stable and unstable situations. So a threshold is where we're going to have instability in some way, shape, or form. So if it's stable, that's not going to be a threshold. If it's unstable or semi-stable, there is a threshold. So for example, let's look at this. So if we're going to draw our phase line from this, our y prime, there's our y. T in this case is going to act like our k, and then we have another drew point at 0. Now in this case, we have a negative out front, so that's going to flip things around. So an easy way to look at this is anytime you have a positive value, so things that are in y prime is positive, it's going to increase. And that's going to increase. And then these are going to all decrease. And now you can label this t over 2 if you want, just as a nice reference point. It doesn't really mean much for us, but it helps add some scale to the graph. Now we're going to draw our graph to have threshold. We're going to check our threshold values. Now we really don't need to worry about this part over here that's negative values, since our t, our y, is a population. So whenever we have a negative population, although theoretically, if you have some other situation you're using this for, yeah, you could have negatives. So now we're going to do our t versus y and show what's happening. So now we have our t value because we're building off of this y-axis. And we're going to draw a dotted line there. Now notice our arrows. That if we are starting above t with y, we increase. If we start between 0 and t, we go to 0. So you can see that in here, that t is a threshold, because things that start above go to infinity and things that start below go to 0. So it's a value. It's a line of demarcation, if you want to think of it. On one side, they go to one limit. On another side, they go to another limit. So you can see that this is a threshold right here because we have things going in different directions from it. So, and often you'll be given your phase line graph, but you can pretty easily get it from your equation to begin with. So let's look at some other ones. And you can even go vice versa too. If you're given your threshold graph, you can find the phase line. So let's do another 7. I'm just going to show a bunch of different ones here. So we'll have a K1. We'll have a K2. And we'll have a K3. This will be a graph of Y. versus t. Let's draw our dotted lines out. So just to demonstrate the different types of stable, unstable, semi-stable is, let's say here, these guys all increase. These guys all come down. These all go up. And these also go up. So right here, this is unstable because nothing is going to, everything's got running away. And this also is marked as a threshold because on the top they go to one limit, on the bottom they go to another limit. K2 will be asymptotically stable. And it's not a threshold because everything's coming towards it. So it doesn't matter if you start above or below, it's going towards it. No distinction. K1 is semi-stable because above it's going away, but below it's going towards it. But this is going to be a threshold type because it has, again, it's a dividing line. Above goes to one place, below goes to another place. And we are going to also include 0, y equals 0, as being unstable. And that would also make it a threshold. Even though we're not looking at what's happening below it, we don't care, but nothing's going towards it. And if it's unstable, or if it's not stable, it's a threshold. So nothing's going towards it. So it could possibly be semi-stable if we knew what was happening for our negative y's, but it's definitely not stable, so we don't have to worry about it. So essentially, if you don't know if something's going towards it, that would be a threshold. If things are just going from above and down, then we could say that that is indeed stable. Now, if we're going to draw our phase line off of this, there's y prime, there's y. We're going to have our K1, we're going to have our K2, we're going to have our K3. When we are between 0 and K1, we're going up to K1. Then in here, we're going up to K2, and we're going also to K2, and then we're going away from K3. So if we're going to draw this, we can look at our graph above to give us hints on what it's going to look like. So in here, y is increasing. So we know we're going to have positives. And let me change this color to make it stand out a little bit more. But then we also have positives there, but we have a 0 right there. So this will come up and stay up. Now it's going to stay positive until we get to the other side of K2. And then once we pass K3, it's going to be positive again because it's increasing. So it's kind of like your curve sketching that you've done before. But if you're given the if we're given the equation, you can come up with both the y prime graph and the t versus y graph. If you're given any one of the graphs, you can find the other graph. And then based on that, you can even find the equation that your y prime is going to have something with a 1 minus y over K1 and 1 minus y over K2 and also 1 minus y over k3. And now you would have situations here. One would be a squared because there's two of them in there, and they have even or odd powers. And then you have a negative or a positive out front, depending on how things work out, and all the algebra stuff of how you would evaluate graphs based on the equation, how do you get the equation based on a graph. But it's all basic stuff from classes long ago. But anyway, general idea, finding your thresholds, finding your stability, instability, semi-stability, and going from there.